Erwin Schrödinger's contributions to quantum mechanics cannot be overstated. The world of physics, particularly at the subatomic level, was transformed thanks to his groundbreaking work. Before Schrödinger's time, the understanding of matter and energy was largely governed by classical mechanics, which worked beautifully for large objects like planets and cars, but failed to explain phenomena at the atomic and subatomic level. The world was still operating largely under the laws of Newton, with the certainty that objects existed in one place at a time, following clear trajectories. But in the 20th century, this certainty was shattered as physicists began to peer into the atomic and subatomic worlds, where the rules of the game seemed entirely different. Schrödinger's work was born from the realization that classical mechanics simply couldn't describe the bizarre behavior of tiny particles such as electrons, which seemed to behave both as particles and waves. Physicists at the time, like Max Planck and Albert Einstein, were already familiar with the quantum nature of energy and light. Planck's work on blackbody radiation and Einstein's explanation of the photoelectric effect were the building blocks that revealed the world wasn't as predictable and deterministic as once thought. Still, there was a massive gap in the understanding of how particles themselves behaved when not being observed. The prevailing theories, which were primarily particle-centric, seemed incomplete. The culmination of this uncertainty led to the development of quantum theory. Schrödinger, along with several other scientists, was integral to giving it a clearer mathematical framework. His primary contribution, the wave equation, sought to resolve a fundamental problem: how to predict the behavior of particles that seem to exist in a haze of possibilities rather than as defined objects. Schrödinger's wave equation emerged as a key equation in quantum mechanics, akin to Newton's laws in classical mechanics. This equation, which described how the quantum state of a physical system changes over time, introduced the concept of the wave function. In simple terms, the wave function was a mathematical description of the probabilities of where a particle could be found at any given time. It suggested that particles, at the quantum level, do not have fixed positions and velocities until they are measured. Instead, they exist in a cloud of possibilities, with each possibility having a certain probability of becoming the reality when observed. Schrödinger's wave equation provided a mathematical foundation that could describe the behavior of quantum systems and opened the door to understanding how matter behaves at the atomic and subatomic levels. This was a radical departure from classical physics, which treated objects as having specific, deterministic properties that could be precisely measured. In the world Schrödinger described, these properties could only be described probabilistically until they were observed. The wave equation helped lay the groundwork for much of modern physics and mathematics, including the development of quantum mechanics, quantum field theory, and quantum computing. The implications of Schrödinger's work were profound. His wave equation helped explain why atoms didn't collapse under the forces pulling their electrons inward. It allowed physicists to understand atomic orbitals and the arrangement of electrons around atoms. The wave function also enabled scientists to predict the behavior of particles in quantum systems, from electrons in atoms to photons of light. Schrödinger's equation not only helped physicists understand the physical world at its most fundamental level, but also suggested that there was much more to reality than what could be directly observed. But Schrödinger's work didn't stop with the wave equation. One of the most famous aspects of his legacy is his thought experiment, Schrödinger's cat, which he devised in 1935 to demonstrate the strange consequences of quantum mechanics. In the thought experiment, Schrödinger used a cat placed in a box with a radioactive substance that could decay and release poison. According to the principles of quantum mechanics, until the box was opened and the cat was observed, the cat would be in a superposition of two states, alive and dead. This paradox was intended to illustrate the strange implications of quantum theory and to highlight the tension between quantum mechanics and the reality we experience. Schrödinger's cat thought experiment may have been a theoretical construct, but it forced the scientific community to confront the central issue of quantum theory, the role of the observer. The paradox raised profound questions about whether the act of observing a system could change its state. In classical mechanics, observation did not affect the state of an object. A ball rolling down a hill would continue to roll, regardless of whether anyone was watching. But in the quantum world, it seemed that the act of measurement or observation forced a system to choose a state from a range of possibilities. This issue of observation versus reality is a core question in the philosophy of science and remains unresolved to this day. As Schrödinger's wave equation began to gain acceptance in the scientific community, it didn't just change the field of physics. It started to shape the way people thought about reality itself. The implications of quantum mechanics were so far-reaching that they stretched beyond the confines of the laboratory and into philosophy, psychology, and even the arts. The idea that reality, at its most fundamental level, could be defined by probabilities rather than certainties, was a radical departure from the deterministic worldview that had dominated for centuries. This shift in thinking was echoed in the philosophical musings of Schrödinger and his contemporaries. Many physicists were deeply concerned about the philosophical implications of quantum mechanics, and Schrödinger, in particular, was reluctant to fully embrace the strange conclusions that were being drawn from the theory. He was one of the first to recognize the paradoxes and uncertainties inherent in quantum mechanics, and he became somewhat disillusioned with the Copenhagen interpretation, which held that quantum systems could exist in multiple states until they were observed. Schrödinger was more inclined toward a deterministic view, one in which the world was governed by underlying laws that could, in theory, be understood and predicted. The concept of quantum indeterminacy, where particles could exist in multiple states until measured, was deeply unsettling to him. Despite his reservations about some aspects of quantum mechanics, Schrödinger's contributions were indispensable. His work provided a framework for understanding the quantum world in a way that had never been done before. His equation laid the groundwork for future advances in quantum physics, including the development of quantum field theory and the later work on quantum computers. Schrödinger's influence was not confined to the scientific community. His ideas also found their way into popular culture, inspiring generations of thinkers, artists, and writers. The iconic image of Schrödinger's cat, in particular, became an emblem of the bizarre and often paradoxical nature of quantum mechanics. One of the most fascinating aspects of Schrödinger's legacy is the extent to which his work continues to shape scientific exploration today. Schrödinger's equation remains one of the core principles of quantum mechanics, and his thoughts on the observer effect and quantum uncertainty continue to influence debates on the interpretation of quantum theory. His wave function, which initially described the behavior of subatomic particles, has since been expanded upon to explain everything from the behavior of light to the interaction of elementary particles. Schrödinger's work also paved the way for practical applications that have revolutionized technology. Quantum mechanics, once a purely theoretical discipline, has given birth to a number of cutting-edge technologies, including semiconductors, lasers, and medical imaging devices. In recent years, Schrödinger's theories have even found applications in the emerging field of quantum computing, where the superposition of states, a key element of Schrödinger's work, is being harnessed to create powerful new computational systems. Quantum mechanics, born from Schrödinger's wave equation, has evolved from a strange and abstract concept into a highly productive and practical field of study. Yet, for all the advancements in technology and understanding, Schrödinger's work has not lost its philosophical allure. The fundamental questions that quantum mechanics raises questions about the nature of reality, the role of observation, and the limits of human knowledge continue to fascinate not just physicists, but people from all walks of life. In this way, Schrödinger's contributions remain as profound and relevant today as they were when he first put pen to paper. Schrödinger's legacy also opens up a broader discussion about the human relationship with knowledge and the limitations of perception. His work pushed the boundaries of human understanding to a place where the very nature of reality itself became uncertain. While Schrödinger's wave equation had a profound mathematical and physical basis, it also forced society to confront more abstract, philosophical questions about the fabric of existence. What happens when we cannot directly observe something? What does it mean for something to exist when it cannot be directly perceived? In many ways, Schrödinger's theories inspired an era of thought that was not limited to the confines of physics, but extended into metaphysical and philosophical considerations. One of the central ideas in Schrödinger's contributions was the probabilistic nature of quantum mechanics, as demonstrated by the wave function. Unlike classical physics, where objects like balls and cars had clear, observable properties that could be measured directly, the behavior of subatomic particles was much more fluid. According to Schrödinger, particles didn't have defined positions or velocities until they were measured. Instead, they existed in a probabilistic state where multiple outcomes were possible. This notion of probability, rather than certainty, was a dramatic shift from the deterministic view of the world that had been accepted since the days of Newton. For Schrödinger, the wave function didn't simply describe how particles behaved in time and space. It provided a picture of the entire quantum world, encapsulating all the possible states that a system could be in. The wave function described a probability cloud, not a single point in space, for where particles like electrons might be located at any given time. This allowed physicists to calculate the likelihood of finding a particle at a specific location, but it could never tell them exactly where the particle was. The act of measuring the particle itself was what collapsed this cloud of probabilities into one reality. The concept of superposition is at the heart of this quantum probabilism. In Schrödinger's view, quantum systems were able to exist in multiple states simultaneously. For example, an electron could be in more than one location at once, or a particle could be in more than one energy state. This phenomenon was one of the many strangenesses of quantum mechanics that set it apart from the more predictable world of classical physics. The famous Schrödinger's cat thought experiment exemplified this idea. In the experiment, the cat inside the box was both alive and dead, existing in a state of superposition, until the box was opened and the state was observed. While Schrödinger's cat is often associated with the paradoxical nature of quantum mechanics, it is important to remember that Schrödinger himself didn't intend it as a literal scenario. Rather, it was a tool to highlight the limitations of the Copenhagen interpretation of quantum mechanics, which had been developed by Niels Bohr and Werner Heisenberg. The Copenhagen interpretation suggested that until a system is observed, it exists in a superposition of all possible states. For Schrödinger, this was a deeply unsatisfactory explanation of reality, one that appeared to conflict with our everyday experiences of the world. The idea that the cat could be both alive and dead until the box was opened seemed absurd to him, yet it perfectly illustrated the inherent contradictions in quantum theory. Schrödinger's disagreement with the Copenhagen interpretation reflected his broader philosophical stance on quantum mechanics. He believed that the wave function, as it was formulated, could not be the final answer to understanding reality. He favored a more deterministic view of the universe, one in which the behavior of particles could be fully understood and predicted if we had enough information. This view aligned more closely with the classical physics of Newton, where the universe operated like a well-oiled machine, with everything governed by fixed laws. Schrödinger was deeply skeptical of the Copenhagen interpretation, as he believed it introduced an element of randomness and uncertainty into the universe that was not only unhelpful, but potentially misleading. Yet, despite his reservations about some aspects of quantum theory, Schrödinger's influence on the development of modern physics cannot be denied. His wave equation formed the backbone of the emerging quantum field theory, and his ideas about the wave function and superposition continue to be central to contemporary quantum research. Schrödinger's wave equation is still taught in every physics department around the world, and it remains a key piece of the quantum puzzle that continues to be worked on by scientists today. The relationship between Schrödinger's work and the broader field of quantum mechanics also underscores the evolution of physics as a discipline. In many ways, Schrödinger's contributions were part of a larger movement in physics that sought to reconcile the findings of quantum mechanics with the well-established theories of classical mechanics. While classical mechanics had been extraordinarily successful in explaining the behavior of macroscopic objects, it had proved inadequate for describing phenomena on the atomic and subatomic levels. Schrödinger, along with other physicists like Heisenberg and Bohr, was part of a new generation of scientists who sought to understand the behavior of particles that existed far outside the realm of everyday experience. In this way, Schrödinger's work had an indelible influence on the development of modern physics. His wave equation and his ideas about quantum probability laid the foundation for the later development of quantum electrodynamics, QED, and quantum chromodynamics, QCD, the two key theories that describe the fundamental forces of nature. His work has also been instrumental in the development of quantum computing, a field that is poised to revolutionize technology in the 21st century. The principles of superposition and entanglement, first explored by Schrödinger and his colleagues, are the cornerstone of quantum computing, where qubits can exist in multiple states simultaneously and perform computations exponentially faster than classical computers. Beyond the technical and scientific contributions, Schrödinger's work also had a profound effect on the philosophical and cultural landscape. His famous thought experiments, particularly the cat paradox, captured the imagination of not only scientists but also artists, writers, and thinkers. Quantum mechanics, with its strange and paradoxical implications, opened up a new way of thinking about the universe and our place within it. Schrödinger's exploration of the uncertainty and indeterminacy of the quantum world forced society to confront the limits of human knowledge, challenging the idea that we can fully understand or predict the world around us. One of the most enduring aspects of Schrödinger's legacy is how his work continues to resonate with people today. Schrödinger's cat remains a symbol of the strange, unknowable nature of quantum mechanics, and it serves as a reminder that even in the world of cutting-edge science, there are still many mysteries that remain unsolved. Schrödinger's contributions continue to inspire new generations of scientists and philosophers who are striving to answer the fundamental questions about the nature of reality and the limits of human understanding. Schrödinger's work also holds an important lesson for the relationship between science and the broader public. His work showed that science is not just about solving problems or discovering new facts. It is also about challenging our preconceived notions and asking difficult questions about the world around us. The strange and counterintuitive nature of quantum mechanics may seem alien to many, but Schrödinger's work serves as a reminder that science is ultimately a journey of discovery, one that challenges us to think in new ways and to never settle for simple answers. Today, Schrödinger's wave equation and the quantum mechanics he helped develop are deeply embedded in the fabric of modern science and technology. From the technology in our smartphones to the complex models used in particle physics, Schrödinger's ideas continue to shape the future of science and technology. Yet, for all the advances in quantum theory, the fundamental questions Schrödinger raised about the nature of observation, reality, and knowledge continue to intrigue and challenge scientists. Schrödinger was not just a physicist, he was a visionary who changed the way we see the world, forever altering our understanding of the universe's deepest truths. The famous Schrödinger's cat thought experiment remains one of the most iconic and perplexing contributions to quantum mechanics. It was not a real experiment in the laboratory sense, but rather a thought experiment, an intellectual exercise designed to demonstrate the strange and paradoxical nature of quantum mechanics. Schrödinger introduced the cat in 1935, at a time when quantum theory was still in its infancy, to illustrate the theoretical implications of quantum superposition, a concept central to quantum mechanics. Schrödinger's idea was simple yet profound. He asked his audience to imagine a cat inside a sealed box. Inside the box, there was a radioactive substance, which has a 50% chance of decaying in a given time frame. If the substance decayed, it triggered the release of poison that would kill the cat. If it did not decay, the cat would remain alive. The key element of the thought experiment was that, according to quantum mechanics, until the box was opened and the system was observed, the radioactive substance was both decayed and not decayed, meaning the cat was both alive and dead at the same time. This situation was a result of quantum superposition, where particles or systems can exist in multiple states simultaneously until they are measured or observed. The paradox of the Schrödinger's cat thought experiment lay in the contradiction it presented. In our everyday experience, we never encounter situations where something can be both alive and dead at the same time. When we look at a cat, we can say with certainty whether it is alive or dead. But in the quantum world, until we measure the system, the state of the cat is described by a wave function, a mathematical expression of the probabilities of all possible outcomes. This wave function exists in a superposition of both alive and dead states, with each state having a certain probability. It is only when an observer opens the box and measures the system that the wave function collapses into one definite state. The cat is either alive or dead. The paradoxical nature of Schrödinger's cat brought to light the strangeness and counterintuitive aspects of quantum mechanics. According to the Copenhagen interpretation of quantum mechanics, proposed by Niels Bohr and Werner Heisenberg, a quantum system exists in a superposition of multiple states until it is measured. At that point, the wave function collapses, and the system takes on a definite value. However, this interpretation was troubling to Schrödinger, who found it difficult to reconcile with our everyday experience of the world. For him, the idea that the cat could be both alive and dead seemed absurd, yet it was a logical consequence of the mathematical framework of quantum mechanics. Schrödinger's cat became a symbol of the weirdness of quantum theory, illustrating how quantum mechanics defies our classical intuitions about the world. The thought experiment was never meant to be taken literally. Instead, it was a way to point out the conceptual problems with the Copenhagen interpretation. Schrödinger himself was critical of the interpretation, which he felt was incomplete. He believed that the theory failed to provide a clear picture of what was actually happening at the quantum level. To Schrödinger, the idea that an observer's intervention could determine the state of a system was deeply unsatisfactory. In his view, the quantum world should be governed by deterministic laws, just as the classical world was. Despite his reservations about the Copenhagen interpretation, Schrödinger's work on the thought experiment led to profound insights into the nature of quantum mechanics. The paradox of the cat has inspired generations of physicists and philosophers to ponder the role of observation and measurement in determining the reality of a quantum system. The question of whether the wave function represents an actual physical reality or merely a tool for predicting probabilities remains a central debate in quantum mechanics. Schrödinger's cat also raised important questions about the nature of reality itself. In the macroscopic world, objects are clearly either in one state or another. A cat is either alive or dead, a car is either parked or in motion, and so on. But in the quantum world, things seem to exist in multiple states at once. This is not just a philosophical issue, it has real implications for the way we understand the universe. If quantum mechanics tells us that particles can exist in multiple states simultaneously, what does that say about the fundamental nature of reality? Does reality exist independently of our observations, or is it, as the Copenhagen interpretation suggests, in some sense created by the act of measurement? These questions have led to various interpretations of quantum mechanics, each attempting to resolve the paradoxes and contradictions that arise when we try to apply quantum theory to the everyday world. One of the most famous alternative interpretations is the many worlds interpretation, proposed by Hugh Everett III in 1957. According to this interpretation, all possible outcomes of a quantum measurement actually occur, each in a separate branch of the universe. In the case of Schrödinger's cat, the universe would split into two branches, one where the cat is alive, and one where the cat is dead. Both realities exist, but they are in different, non-interacting branches of the universe. The many worlds interpretation avoids the problem of wave function collapse by suggesting that all possibilities are realized in a vast multiverse of parallel realities. Another interpretation, known as the de Broglie-Bohm theory or pilot wave theory, proposes that particles have definite positions and velocities at all times, even when they are not being observed. In this view, the wave function is not a complete description of reality, but rather a mathematical tool that guides the particle's motion. The de Broglie-Bohm theory offers a more intuitive, classical picture of the quantum world, but it is not as widely accepted as the Copenhagen interpretation or the many worlds interpretation. While Schrödinger's cat was designed to highlight the paradoxes of quantum mechanics, it also pointed to a deeper philosophical issue, the role of the observer in shaping the nature of reality. The question of whether the act of observation affects the system being observed is still a subject of intense debate. Some physicists argue that the observer plays a crucial role in determining the outcome of a quantum experiment, while others maintain that the observer is merely revealing an underlying reality that exists independently of observation. The Schrödinger's cat thought to experiment has had a lasting impact on both the field of physics and the broader cultural imagination. It has become a symbol of the strange and paradoxical nature of quantum mechanics, and it continues to inspire discussions about the limits of human knowledge and the mysteries of the universe. Schrödinger's work also highlights the tension between the abstract, mathematical world of quantum mechanics and the everyday classical world we experience. It forces us to confront the limitations of our understanding of reality and challenges us to think more deeply about the nature of observation, measurement, and existence itself. Schrödinger's cat, while a thought experiment, has also influenced the development of quantum technologies. Quantum superposition and entanglement, key concepts explored through the thought experiment, are foundational to the emerging field of quantum computing. In quantum computers, qubits can exist in multiple states at once, allowing them to process vast amounts of information simultaneously. The potential for quantum computing to revolutionize fields such as cryptography, artificial intelligence, and materials science is immense, and Schrödinger's cat serves as a reminder of the power and potential of quantum mechanics. While the paradox of Schrödinger's cat remains unresolved, it has played a crucial role in shaping our understanding of the quantum world. It has inspired new theories, new experiments, and new ways of thinking about the universe. Schrödinger's contribution to quantum mechanics, through his wave equation and his thought experiment, has left an indelible mark on the history of science. His work has not only advanced our understanding of the subatomic world, but has also challenged us to think more deeply about the nature of reality itself. The strange implications of Schrödinger's cat thought experiment have not only reshaped our understanding of quantum mechanics, but have also forced philosophers and physicists alike to reconsider the nature of reality itself. At the heart of the thought experiment is the quantum concept of superposition, where a system, such as the radioactive atom in Schrödinger's scenario, can exist in a combination of multiple states until it is observed or measured. This was a radical departure from classical physics, where objects, like cats, could only exist in one state at a time, alive or dead, but not both. In quantum mechanics, however, it seemed that the cat's fate was intrinsically tied to the behavior of subatomic particles, which, according to Schrödinger's interpretation, could exist in overlapping states, existing as both alive and dead until measured. This paradox highlights the tension between the abstract, probabilistic world of quantum mechanics and the concrete reality of everyday experience. The key question that Schrödinger's thought experiment raised was whether the quantum mechanical description of the universe, governed by probabilities and uncertainties, truly applies to macroscopic objects like a cat. Quantum systems are usually described using wave functions, which represent the probabilities of finding a particle in different states. Until the system is measured, it exists in a superposition, a state of all possible outcomes, where every potential result coexists. In the case of Schrödinger's cat, both the cat's life and death exist simultaneously, each with a certain probability. However, the moment an observer opens the box and measures the cat's state, the superposition collapses, and the cat assumes one of the two possible states, alive or dead. Schrödinger himself was deeply uncomfortable with this conclusion. His motivation for creating the thought experiment was not to argue that a cat could actually be both alive and dead, but rather to highlight the absurdity of applying quantum mechanics to everyday objects. Schrödinger was attempting to show the limits and paradoxes of the Repter's steel, Copenhagen interpretation, which was the prevailing theory at the time. According to the Copenhagen interpretation, quantum particles do not have definite properties until they are measured, and the act of measurement plays a critical role in determining the state of the system. In Schrödinger's view, applying this interpretation to macroscopic objects, like cats, seemed nonsensical. After all, we do not see objects around us existing in superposition. Things are either one thing or another, not both at once. The paradox posed by Schrödinger's cat raised important questions about the relationship between the microscopic quantum world and the macroscopic classical world. At the heart of Schrödinger's critique was the issue of observation. In the Copenhagen interpretation, the wave function describing a quantum system only provides the probability of finding a particle in a particular state. The moment an observer interacts with the system, by measuring it or observing it, the wave function collapses into one definite state, a phenomenon known as wave function collapse. The observer is, therefore, an active participant in determining the outcome of a quantum event. Schrödinger found this idea unsettling, as it suggested that reality is not fully defined until it is observed. He was uncomfortable with the notion that an unobserved system could exist in a probabilistic state and that the very act of measurement determines which possibility becomes reality. Schrödinger's dissatisfaction with the Copenhagen interpretation led him to explore alternative ideas about the nature of reality. He was not alone in this. Many physicists, including Albert Einstein, also had reservations about the Copenhagen view of quantum mechanics. Einstein famously referred to quantum mechanics as "God does not play dice with the universe," expressing his belief that there must be underlying deterministic laws governing the behavior of particles, even if we did not yet understand them. Schrödinger shared this skepticism. and while he made crucial contributions to quantum mechanics, he was not convinced that the theory fully captured the nature of the universe. He believed that quantum mechanics could be part of a larger, more complete theory that would restore determinism to the universe. Over time, Schrödinger's doubts about the Copenhagen interpretation have been echoed by many other interpretations of quantum mechanics. The many-worlds interpretation, for example, posits that when a quantum system is measured, all possible outcomes occur, each in a separate branch of the universe. According to this view, there is no wave function collapse. Every possible state of the system is realized in a different branch of reality, and each observer exists in one of these branches. In the case of Schrödinger's cat, the many-worlds interpretation would suggest that both the alive and dead cat exist in separate, non-interacting branches of the universe, each observer being part of one of these realities. While this interpretation avoids the paradox of wave function collapse, it introduces the unsettling idea of an ever-expanding multiverse of realities, one where every possibility is realized. Alternatively, the de Broglie-Bohm theory, or pilot wave theory, offers a deterministic view of quantum mechanics that avoids the need for wave function collapse. According to this theory, particles have well-defined positions and velocities at all times, even when they are not being observed. The wave function still plays a role in guiding the motion of particles, but it does not determine the system's state in a probabilistic manner. Instead, the wave function is seen as a mathematical tool that directs the particle along a definite path. The de Broglie-Bohm theory offers a more classical picture of quantum mechanics and provides an alternative to the indeterminacy introduced by the Copenhagen interpretation. However, it has not been as widely accepted as other interpretations, and it faces challenges in terms of its empirical verification. Schrödinger's cat has also influenced modern debates about the nature of quantum measurement. Some physicists argue that the act of measurement does not involve an observer in the traditional sense. Instead, they propose that quantum systems interact with their environment, leading to what is known as decoherence. In this view, the wave function of a quantum system is entangled with the environment, and the act of measurement simply reflects the system's entanglement with its surroundings. This interpretation suggests that the classical world emerges naturally from the quantum world as a result of entanglement and decoherence, without the need for an observer to collapse the wave function. Decoherence has become a key concept in the study of quantum systems and is crucial in fields like quantum computing, where quantum coherence must be maintained for qubits to perform computations. Despite the variety of interpretations that have emerged since Schrödinger's time, the Schrödinger's cat thought experiment remains a central topic in discussions of quantum mechanics. It forces us to confront the core issues of the theory: the role of the observer, the nature of measurement, and the relationship between the quantum and classical worlds. While we may never be able to perform a real experiment involving a cat in a box, the paradox of Schrödinger's cat has served as a powerful tool for pushing the boundaries of scientific understanding. It has raised profound questions about the nature of reality, the limits of human knowledge, and the fundamental structure of the universe. Schrödinger's legacy also extends beyond the realm of physics. His thought experiment has captured the public imagination and has become an enduring symbol of the strange and mysterious nature of quantum mechanics. Schrödinger's cat is not just a paradox, it is a metaphor for the uncertainty and complexity that lie at the heart of the quantum world. It serves as a reminder that the universe is far stranger and more mysterious than our everyday intuitions would suggest. The cat, both alive and dead, is an image that challenges our understanding of what is real and what is possible. In conclusion, the Schrödinger's cat thought experiment is one of the most important and enduring contributions to the study of quantum mechanics. It has forced physicists to confront the paradoxes of quantum theory and has inspired numerous alternative interpretations of the theory. The thought experiment raises fundamental questions about the nature of reality, the role of the observer, and the limits of human knowledge. Schrödinger's cat continues to be a powerful symbol of the strange, uncertain, and counterintuitive nature of the quantum world. While the paradox may never be fully resolved, it will continue to serve as a touchstone for future generations of scientists, philosophers, and thinkers who seek to understand the deepest mysteries of the universe. Schrödinger's belief in the wave function as a representation of the quantum state of a system had a profound impact on how physicists understand the behavior of particles. In classical physics, particles were viewed as distinct objects with definite properties, such as position and momentum, that could be precisely measured at any given time. This deterministic view was rooted in the work of Isaac Newton, whose laws of motion governed the behavior of objects on a macroscopic scale. However, as scientists began exploring the subatomic world, it became apparent that the classical understanding of particles did not apply to the behavior of atoms and smaller particles. The concept of the wave function was Schrödinger's contribution to bridging the gap between classical mechanics and quantum mechanics. Schrödinger's wave function is a mathematical description that encapsulates all the possible states of a quantum system. The wave function itself is a complex number, and the square of its absolute value gives the probability distribution of finding a particle in a particular state or location. This represented a significant shift in how scientists thought about particles. Unlike in classical mechanics, where the position and velocity of an object could be precisely determined, the wave function only describes the probability of a particle being in a certain state, not the exact state itself. This probabilistic nature of quantum mechanics, introduced by Schrödinger, was revolutionary. It implied that, until measured, particles do not exist in a single, well-defined state. Instead, they exist in a superposition of multiple possible states. This superposition is described by the wave function, and it collapses into one of the possible outcomes only when a measurement is made. This is the core principle of the famous wave-particle duality in quantum mechanics, which suggests that particles such as electrons can exhibit properties of both waves and particles, depending on how they are observed. The wave function, in Schrödinger's view, was not just a tool for calculating probabilities. It was a fundamental representation of reality itself. It described a quantum system in its entirety, capturing all the possible configurations of the system. Schrödinger's wave equation, which mathematically described how the wave function evolves over time, became one of the central equations of quantum mechanics, much like Newton's laws in classical mechanics. The equation itself is a partial differential equation that accounts for the changes in the wave function and, by extension, the changes in the probability distribution of particles within a system. For Schrödinger, the wave function was not merely an abstract mathematical construct, it had a physical reality. In his view, the wave function was not just a statistical tool to predict the likelihood of various outcomes. It was a real entity that governed the behavior of quantum systems. He envisioned the wave function as a real physical field, much like the electromagnetic field, which influenced the motion of particles. Schrödinger's equation, therefore, represented a fundamental shift in our understanding of the quantum world. Instead of thinking of particles as individual entities with specific positions and velocities, we now had to think of them as existing in a state of probability, with their exact nature only revealed upon measurement. Schrödinger's ideas had profound implications for the way scientists viewed the universe. Classical mechanics, with its deterministic framework, assumed that the universe operated like a giant clock, with everything moving in precise, predictable ways. If we knew the initial conditions of a system, we could predict its future behavior with certainty. But quantum mechanics, as Schrödinger and others showed, was radically different. The behavior of particles was not deterministic but probabilistic. The idea that particles did not have definite positions until they were measured was a stark departure from classical ideas, which assumed that everything in the universe could be precisely known and predicted. One of the key ideas that Schrödinger's wave function introduced was the concept of uncertainty. In classical physics, it was assumed that if we knew the position and velocity of an object, we could predict its future behavior with perfect accuracy. However, quantum mechanics introduced the idea that, for particles at the quantum level, there is an inherent uncertainty in our ability to know both their position and momentum simultaneously. This uncertainty is captured by the Heisenberg uncertainty principle, which states that the more precisely we try to measure one property of a particle, such as its position, the less precisely we can know the other property, such as its momentum. Schrödinger's wave function, therefore, was not just a description of a quantum system, it was a reflection of the inherent limitations of our knowledge about the quantum world. This uncertainty was not just a limitation of our measurement tools, it was a fundamental aspect of reality. In the quantum world, particles do not have well-defined properties until they are observed. Until a particle is measured, it exists in a superposition of all possible states, with the wave function describing the probabilities of these different states. It is only when an observation is made that the wave function collapses and the particle assumes a definite state. This idea of wave function collapse was one of the most contentious aspects of Schrödinger's theory, as it suggested that the act of observation played a crucial role in determining the outcome of a quantum system. Schrödinger himself was deeply uncomfortable with this idea, as it seemed to imply that reality was not fixed until it was observed, which contradicted his belief in a deterministic universe. Despite Schrödinger's discomfort with the idea of wave function collapse, his wave equation provided a powerful tool for understanding the behavior of quantum systems. It allowed scientists to calculate the probabilities of different outcomes in quantum experiments and predict the behavior of particles with remarkable accuracy. Schrödinger's equation was used to explain phenomena such as the energy levels of electrons in atoms, the behavior of light and matter, and the interactions between particles in high-energy physics. His work laid the foundation for much of modern quantum mechanics, and his equation is still used today in research on quantum systems, from atoms and molecules to superconductors and quantum computers. Schrödinger's wave function also had implications for the development of quantum chemistry. By using his equation, chemists could describe the behavior of electrons in atoms and molecules and predict the chemical properties of different substances. Schrödinger's work helped to explain the stability of atoms and the structure of the periodic table, providing a theoretical framework for understanding chemical bonding and reactions at the quantum level. This led to the development of quantum chemistry as a field in its own right, which has had a profound impact on fields such as materials science, nanotechnology, and drug design. The impact of Schrödinger's wave function extended beyond the confines of theoretical physics and chemistry. In the decades following Schrödinger's work, the principles of quantum mechanics began to be applied to a wide range of technologies. The development of quantum electronics, which includes technologies such as semiconductors and lasers, was based on the principles of wave-particle duality and wave functions. Schrödinger's work laid the groundwork for the development of modern electronics, telecommunications, and computer technologies, which have transformed the world in the 20th and 21st centuries. Schrödinger's contributions also influenced the development of quantum computing, which relies on the principles of superposition and entanglement, both of which are tied to the wave function. Quantum computers use quantum bits, or qubits, which can exist in multiple states at once, enabling them to process information in parallel and solve complex problems much faster than classical computers. Schrödinger's wave function, which describes the probabilistic nature of quantum systems, is a key concept in quantum computing, as it allows qubits to perform computations that would be impossible for classical bits. Schrödinger's ideas have continued to shape the development of quantum theory and technology to this day. His wave equation and the concept of the wave function have become central to the study of quantum mechanics, and his work remains foundational to much of modern physics. Schrödinger's belief that the wave function represents the true state of a quantum system has had lasting implications for how we understand the nature of reality. While Schrödinger himself was uncomfortable with some of the philosophical implications of quantum mechanics, his work paved the way for the ongoing exploration of the quantum world. His contributions continue to inspire scientists, philosophers, and engineers as they work to unlock the mysteries of the universe and harness the power of quantum technologies. Schrödinger's legacy, particularly through his wave function and its implications, continues to shape the field of quantum mechanics and our understanding of reality. While Schrödinger's wave function and the principles of quantum mechanics have proven highly successful in explaining the behavior of subatomic particles, they have also raised some profound and ongoing philosophical and conceptual questions. One of the key questions revolves around the nature of reality itself. What does it mean for a system to be in a superposition of states? Does the wave function represent the actual state of a system, or is it merely a mathematical tool for predicting outcomes? The interpretation of the wave function has been one of the most debated aspects of quantum mechanics. Schrödinger's own view on the wave function was that it had a physical reality. He believed that the wave function described the true state of a system, and he saw it as a real physical field, akin to the electromagnetic field. In this view, the wave function was not just a probabilistic description of a quantum system, it was an actual entity that governed the behavior of particles and systems. This interpretation suggests that quantum systems, in their entirety, are governed by the wave function, which encodes the probabilities of all possible states the system could be in. However, other interpretations of quantum mechanics take a different view. One of the most widely accepted interpretations is the Copenhagen interpretation, which was developed by Niels Bohr and Werner Heisenberg in the 1920s. According to the Copenhagen interpretation, the wave function is not a physical entity in itself, but merely a tool for predicting the probability of various outcomes. In this interpretation, the wave function represents the potential states of a system, but it is not a reflection of the system's actual state until a measurement is made. Upon measurement, the wave function collapses into one of the possible states, and the system takes on a definite property. This interpretation is often described as the measurement problem because it implies that the act of measurement plays a fundamental role in determining the state of a quantum system. The measurement problem highlights one of the central paradoxes of quantum mechanics, the idea that particles exist in multiple states at once, as described by the wave function, until they are measured. In classical physics, objects have definite properties that can be measured directly, but in quantum mechanics, particles do not have definite properties until they are observed. This leads to a strange and counterintuitive idea. The act of observation itself determines the outcome of a quantum event. Schrödinger's cat, with its superposition of a living and dead cat, perfectly illustrates this paradox. Until the box is opened and the cat is observed, it exists in a superposition of both states, alive and dead. This paradox challenges our classical intuition about the world, where objects exist in one state or another, but never both at the same time. One interpretation of this paradox is the many worlds interpretation, proposed by Hugh Everett III in the 1,950 seconds. According to the many worlds interpretation, when a quantum system is measured, all possible outcomes occur, but in separate, non-interacting branches of the universe. In this view, there is no collapse of the Fourier wave function. Instead, the universe splits into multiple branches, each corresponding to one of the possible outcomes of the measurement. In the case of Schrödinger's cat, the universe splits into two branches, one where the cat is alive and one where the cat is dead. Both outcomes occur, but they exist in separate branches of reality, each observer experiencing only one of these realities. The many worlds interpretation avoids the measurement problem by suggesting that all possible outcomes of a quantum measurement actually happen, each in its own separate universe. This interpretation eliminates the need for wave function collapse and the role of observation in determining the state of a system. However, the many worlds interpretation raises its own set of philosophical and conceptual issues. For one, it implies the existence of an enormous number of parallel universes, each with its own version of reality. This is difficult to test or observe, and as a result, the many worlds interpretation has not been widely accepted by the scientific community, despite its intriguing implications. Another alternative interpretation is the de Broglie-Bohm theory, or pilot wave theory, which was developed by Louis de Broglie and David Bohm in the early 20th century. The de Broglie-Bohm theory suggests that particles have definite positions and velocities at all times, even when they are not being observed. In this view, the wave function does not describe the actual state of the particle, but instead guides the particle along a definite trajectory. The wave function is still a key part of the theory, but it does not collapse upon measurement. Instead, it serves as a pilot wave, influencing the motion of the particle but not determining its exact position. The de Broglie-Bohm theory provides a deterministic view of quantum mechanics, in contrast to the probabilistic nature of the Copenhagen interpretation. However, like the many worlds interpretation, it has not gained widespread acceptance, and it faces challenges in terms of experimental verification. The ongoing debates over the interpretation of quantum mechanics highlight the fact that, while Schrödinger's wave function has been incredibly successful in predicting the behavior of quantum systems, there is still no consensus on the nature of the wave function itself. Does it represent a real physical field, as Schrödinger believed, or is it simply a tool for calculating probabilities, as the Copenhagen interpretation suggests? Is the wave function a reflection of reality, or is it merely a mathematical abstraction that helps us predict outcomes? These questions remain unresolved, and they lie at the heart of some of the deepest philosophical debates in modern physics. Schrödinger's wave function also raises questions about the nature of time and causality in quantum mechanics. In classical physics, the laws of motion are deterministic. If we know the initial conditions of a system, we can predict its future behavior with perfect accuracy. However, in quantum mechanics, the future behavior of a system is not deterministic but probabilistic. The wave function evolves over time, and the probability distribution of a particle's position changes as a result. This probabilistic evolution is governed by the Schrödinger equation, which describes how the wave function evolves over time. Unlike classical mechanics, where time is an independent parameter that governs the motion of objects, in quantum mechanics, time is treated as a dynamic variable that influences the evolution of the wave function. The probabilistic nature of quantum mechanics has led to a shift in how we understand causality. In classical mechanics, causality is a straightforward concept. Causes lead to effects, and the future can be predicted from the past. However, in quantum mechanics, causality is not as clear-cut. The future behavior of a quantum system is determined by probabilities, and the outcome of a measurement is not certain until it is observed. This challenges our classical understanding of causality and raises questions about whether causality operates differently at the quantum level. Despite the challenges and paradoxes that quantum mechanics presents, Schrödinger's wave function has been extraordinarily successful in explaining the behavior of subatomic particles and in providing a framework for the development of quantum technologies. Quantum mechanics, with its probabilistic nature and the role of the wave function, has been essential in the development of technologies such as semiconductors, lasers, and magnetic resonance imaging (MRI). Quantum mechanics also underpins the emerging field of quantum computing, where the principles of superposition and entanglement are harnessed to perform complex computations that would be impossible with classical computers. Schrödinger's legacy in quantum mechanics also extends beyond his wave equation and its applications. His ideas about the role of the observer in determining the state of a system have led to deep philosophical debates about the nature of reality and the limits of human knowledge. Schrödinger's work has influenced not only the development of quantum theory, but also our understanding of the universe itself. His wave function is not just a tool for predicting the behavior of particles, it is a representation of the underlying reality of the quantum world. Schrödinger's contributions continue to inspire physicists, philosophers, and scientists in many fields as they seek to understand the nature of the universe and the mysteries of the quantum realm. In conclusion, Schrödinger's belief in the wave function and its fundamental role in quantum mechanics has had a profound and lasting impact on science. His work has revolutionized our understanding of the subatomic world, and his wave equation remains one of the central equations in quantum mechanics. Schrödinger's contributions have also raised important philosophical questions about the nature of reality, the role of observation, and the limits of human knowledge. While many of these questions remain unanswered, Schrödinger's work has paved the way for future discoveries and has shaped the development of quantum theory and technology. His legacy continues to inspire and challenge scientists, philosophers, and thinkers to explore the mysteries of the quantum world. Schrödinger's idea that observation plays a crucial role in collapsing quantum states into one reality is a concept that fundamentally challenges our understanding of the universe. In classical physics, objects and events are assumed to exist in a definite state, independent of whether they are observed. For instance, if you are watching a ball rolling down a hill, its position and velocity are clear and measurable. But in the quantum world, the situation is far more complicated. According to quantum mechanics, until a particle is observed, it exists in a superposition of all possible states. Only when we make a measurement or an observation does the system collapse into a single state, revealing a definite outcome. This idea became one of the central features of Schrödinger's thoughts on quantum mechanics, particularly in his critique of the Copenhagen interpretation. In the Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, the observer plays a critical role in the quantum process. Before observation, quantum particles exist in a range of probabilities rather than definite states. The wave function, which is a mathematical description of all the possible states of a system, reflects this uncertainty. Once an observation is made, the wave function collapses and the particle adopts one specific state. This introduces an important philosophical question. If the act of observation is what brings about the collapse, does reality exist independently of our Hurston observation, or is it created by it? This paradox was deeply unsettling to many physicists, including Schrödinger, who found it difficult to accept that the universe depended on human observation to manifest its reality. One of the most profound implications of this idea is the so-called measurement problem. In quantum mechanics, the measurement process does not simply reveal a pre-existing reality, it actually seems to determine it. For example, in the famous double-slit experiment, particles such as electrons exhibit wave-like behavior when not observed. They can pass through two slits simultaneously, creating an interference pattern on a screen behind them. However, when observed, they behave like particles and pass through one slit only, collapsing the wave-like behavior into a definite position. This observation-driven collapse is known as wave function collapse. The question then arises: does the universe exist in a superposition of all possible states until we observe it, or is the act of observation creating the state we perceive? Schrödinger was deeply critical of this interpretation. He felt that it lacked a physical explanation for the act of collapse, and that the wave function should describe a real, physical system rather than just a tool for predicting outcomes. His discomfort with the observer-driven collapse of the wave function led him to create his famous thought experiment, Schrödinger's cat, as a way to highlight the absurdity of applying quantum mechanics to the macroscopic world. In the Schrödinger's cat thought experiment, a cat in a box is both alive and dead until someone opens the box and observes it, highlighting the contradictions between the probabilistic nature of quantum mechanics and the certainty we experience in the classical world. Schrödinger's concerns were not simply theoretical. They pointed to a deeper issue about the nature of reality itself. If reality is shaped by observation, how can we reconcile this with our everyday experiences? In classical physics, objects exist in well-defined states, and they behave predictably whether or not we observe them. In the quantum world, however, particles seem to exist in a cloud of probabilities until measured. This observation-driven reality raises fundamental questions about the nature of time, space, and causality. For Schrödinger, this was a sign that quantum mechanics, while powerful in its predictive capacity, could not fully explain the universe in a way that aligned with our understanding of objective reality. In conclusion, Schrödinger's work and his critique of the Copenhagen interpretation underscore the importance of observation in quantum mechanics. The idea that the observer influences the outcome of a quantum experiment challenges our classical understanding of the universe. It forces us to confront the question: does the universe exist independently of observation, or is it shaped by the very act of perceiving it? Schrödinger's concerns about the role of the observer in quantum mechanics remain relevant today, as physicists continue to grapple with the philosophical and conceptual implications of quantum theory. Schrödinger's lasting influence on modern science, particularly in the fields of quantum mechanics, quantum computing, and quantum entanglement, remains undeniable. While Schrödinger is perhaps best known for his wave equation and the thought experiment involving Schrödinger's cat, his contributions laid the groundwork for many of the advancements in quantum physics that have transformed technology and our understanding of the universe. Schrödinger's work, although based in the theoretical realm, sparked a revolution that led to a multitude of practical applications. His equation, which describes how the quantum state of a system changes over time, became the cornerstone of quantum mechanics. It not only refined our understanding of atomic structure and subatomic particles, but also offered solutions to some of the most complex problems in physics. In particular, Schrödinger's wave equation helped explain the behavior of electrons in atoms, a problem that had previously stumped scientists. By treating electrons not as discrete particles, but as wave-like entities, Schrödinger provided a way to predict the locations and energies of electrons in atoms. This explanation formed the basis of modern quantum chemistry, which underpins many scientific fields, from the design of materials to pharmaceutical research. The understanding of atomic structure, which Schrödinger contributed to, has had profound implications for fields like chemistry and materials science, enabling the creation of new materials with specific properties. Without his work, the development of these fields would not have been as advanced as they are today. Schrödinger's influence extended into the realm of quantum computing, where his theories about superposition and quantum entanglement paved the way for the development of new computational systems. Quantum computing uses the principles of quantum mechanics, including the ability for particles to exist in multiple states simultaneously, to perform calculations that would be impossible for classical computers. Schrödinger's concept of the wave function, which describes a system's probabilities and possible states, has been instrumental in the development of quantum algorithms, which could revolutionize industries ranging from cryptography to drug development. The principles Schrödinger laid out are directly responsible for making quantum computing a reality, opening the door to new forms of computation that promise to solve complex problems far beyond the reach of current technology. Another significant area where Schrödinger's work left its mark is quantum entanglement, which remains a crucial concept in quantum mechanics. Entanglement refers to the phenomenon where particles become linked in such a way that the state of one particle instantaneously affects the state of another, no matter how far apart they are. Schrödinger, in fact, coined the term entanglement to describe this phenomenon. This concept has since become foundational to quantum theory, with implications not just for theoretical physics, but for the development of quantum technologies such as quantum cryptography and quantum communication. Entanglement challenges our classical notions of locality and causality, suggesting that information can travel instantaneously across distances, defying our understanding of time and space. Schrödinger's insight into the nature of entanglement has thus become a critical element of the quantum world, influencing not only our theoretical understanding of the universe, but also providing a basis for the next generation of secure communication technologies. Moreover, Schrödinger's work has had a significant philosophical impact, particularly in the context of debates about determinism and the nature of reality. His work has prompted deep discussions about the role of the observer in quantum mechanics and the apparent randomness of quantum systems. The collapse of the wave function upon observation, a phenomenon Schrödinger highlighted, suggests that the act of measurement plays a pivotal role in determining the outcome of quantum events. This observation-driven collapse of states challenges the deterministic worldview that classical physics had established. The idea that the universe exists in a state of uncertainty, with the outcome only determined upon observation, raises questions about the nature of reality itself. Does the universe exist independently of our perception, or is it, in some sense, created by our act of measurement? Schrödinger's contributions to this ongoing debate continue to inspire philosophers, physicists, and thinkers as they explore the profound implications of quantum mechanics for our understanding of reality. Schrödinger's contributions continue to resonate in the present, as his work on the wave equation, quantum mechanics, and related fields remains relevant in cutting-edge research. His ideas have helped shape the modern landscape of physics and have fueled the development of technologies that are transforming the way we live. From quantum computing and encryption to our understanding of the behavior of matter at the atomic level, Schrödinger's work has not only advanced science, but also paved the way for innovations that were once thought to be science fiction. His ideas, both theoretical and philosophical, continue to guide research in quantum mechanics and challenge our understanding of the universe, making him one of the most influential scientists of the 20th century. Schrödinger's enduring legacy extends far beyond the realm of theoretical physics and touches on a variety of modern scientific advancements. His theories on quantum mechanics, particularly his work on wave functions and the probabilistic nature of particles, have played an integral role in shaping the contemporary understanding of the microscopic world. His research provided the foundation for some of the most crucial discoveries in quantum physics and has driven numerous innovations in technology. Schrödinger's insights helped refine the understanding of atomic structures, subatomic particles, and their behaviors, all of which are foundational in modern science. One of Schrödinger's most significant contributions to quantum mechanics was his introduction of the wave function, which describes the quantum state of a system. This mathematical description helps explain how particles, such as electrons, can exist in multiple states at once, a concept known as superposition. Prior to Schrödinger's work, scientists struggled to explain the behavior of particles at the atomic level. Classical physics, which relied on the certainty of an object's position and momentum, was inadequate to describe the uncertainty that characterizes quantum phenomena. Schrödinger's wave function provided the necessary framework for understanding the probabilistic behavior of particles. Instead of assuming that particles had fixed properties, Schrödinger introduced the idea that particles could exist in a cloud of possibilities, each with a specific probability. This was a radical shift that shaped the development of quantum theory and continues to influence modern physics. Schrödinger's work also helped bring clarity to the quantum mechanical concept of energy levels within atoms. In classical physics, electrons were thought to orbit around the nucleus in a predictable, continuous path, much like planets orbiting the Sun. However, when scientists observed atomic behavior, they noticed that electrons did not follow these classical orbits. Instead, they existed in quantized energy states, and this discovery posed a significant challenge to classical theories. Schrödinger's wave equation helped resolve this by describing how electrons could occupy discrete energy levels within an atom. This work not only laid the groundwork for the field of quantum chemistry, but also paved the way for understanding phenomena such as atomic spectra, the interactions between electrons and light, and the nature of chemical bonds. Schrödinger's influence extends well beyond theoretical research and touches on practical applications that have transformed modern life. His work, particularly the understanding of quantum states, led to the development of technologies that were once unimaginable. The rise of quantum electronics, including lasers and semiconductors, can be directly traced to Schrödinger's contributions. These technologies have had a profound impact on everything from telecommunications to medical imaging. Lasers, which are used in everything from barcode scanners to laser surgery, are based on the quantum mechanical understanding of light. Similarly, semiconductors, the backbone of modern computing and electronics, rely on quantum mechanics to function. Schrödinger's wave function provided the mathematical underpinnings for understanding how electrons behave in these materials, which is central to their function in electronic devices. Another area where Schrödinger's work has had far-reaching effects is in the development of quantum computing. Schrödinger's insights into superposition and the probabilistic nature of quantum systems laid the foundation for quantum computing, a field that is poised to revolutionize the technology landscape. Unlike classical computers, which use bits to represent information in one of two states, 0 or 1, quantum computers use qubits, which can exist in multiple states simultaneously due to superposition. This allows quantum computers to process complex computations at a speed and efficiency that classical computers cannot match. Schrödinger's work on wave functions and quantum states directly informs the development of quantum algorithms, which are crucial for solving problems in cryptography, material science, and artificial intelligence. Though quantum computing is still in its early stages, Schrödinger's contributions are a key part of the theoretical framework that supports this transformative technology. Schrödinger's work on quantum entanglement also continues to shape the development of quantum technologies. Entanglement is a phenomenon where particles become correlated in such a way that the state of one particle can instantaneously influence the state of another, regardless of distance. Schrödinger, who coined the term entanglement, recognized the deep implications of this phenomenon, which defies classical concepts of locality and causality. Entanglement has become a central feature in fields like quantum cryptography and quantum communication, where its ability to create secure, unbreakable channels of communication is being harnessed. Schrödinger's early recognition of entanglement helped push the boundaries of quantum mechanics and paved the way for modern quantum information science. Schrödinger's contributions also extend into the realm of philosophy, where his work has sparked debates about the nature of reality and the limits of human knowledge. His thought experiments, particularly the Schrödinger's cat paradox, highlighted the conceptual problems of quantum mechanics and the role of the observer in shaping the quantum state. The paradox posed by Schrödinger's cat, where a cat in a box is both alive and dead until observed, questions the very nature of reality. If quantum systems exist in superposition until measured, what does this mean for the macroscopic world we experience daily? Schrödinger's paradox brought attention to the strangeness of quantum theory and forced physicists and philosophers to confront the philosophical implications of quantum mechanics, particularly the relationship between observation and reality. This question continues to be a source of debate as it challenges the traditional view that the universe exists independently of human perception. In conclusion, Schrödinger's work in quantum mechanics has left an indelible mark on science, technology, and philosophy. His introduction of the wave function provided the framework that transformed our understanding of atomic and subatomic particles. His contributions have led to technological advancements in quantum electronics, quantum computing, and communication systems. Schrödinger's theories have also inspired ongoing philosophical discussions about the nature of reality and the role of observation in shaping the universe. His ideas continue to influence research and innovation today, proving that his work was not only groundbreaking for his time, but also foundational for the future of science and technology. Schrödinger's legacy is one of profound and lasting impact, shaping the quantum revolution that is still unfolding. Schrödinger's cat, a thought experiment proposed by Erwin Schrödinger in 1935, has become one of the most iconic symbols of quantum mechanics. It was conceived not to be a real experiment, but as a theoretical scenario to highlight the paradoxical nature of quantum theory. The thought experiment presents a situation where a cat inside a sealed box is simultaneously alive and dead, based on the behavior of a radioactive atom inside the box. According to quantum mechanics, the atom could either decay or not decay, and until observed, the cat is in a superposition of both states alive and dead at the same time. This paradox challenges our classical intuitions about the world and forces us to confront the complex and counterintuitive nature of quantum mechanics. The cat thought experiment directly addresses the strange concept of quantum superposition, a principle at the heart of quantum theory. Superposition states that particles, such as electrons or photons, can exist in multiple states simultaneously. This is in stark contrast to classical physics, where objects are assumed to exist in one well-defined state at any given time. Schrödinger used the cat as a metaphor to illustrate how quantum particles, until measured, can exist in all possible states at once. In the case of the cat, the idea is that it can be both alive and dead simultaneously until the box is opened, forcing the system to collapse into a single state. This concept of superposition has profound implications for our understanding of reality, as it suggests that the universe is much more probabilistic and uncertain at the microscopic level than we typically experience in the macroscopic world. Schrödinger's cat also touches on the issue of quantum measurement and the observer's role in determining the state of a quantum system. According to the Copenhagen interpretation of quantum mechanics, developed by Niels Bohr and Werner Heisenberg, the wave function, which describes a quantum system's possible states, collapses into a single state only when observed. Before observation, The system exists in a superposition of all possible states. In the case of Schrödinger's cat, it is only when the box is opened and the cat is observed that its state becomes defined alive or dead. This raises a key philosophical question. Does the act of observation play an active role in shaping reality, or is the universe already in a defined state, regardless of whether we observe it? Schrödinger himself found this idea troubling and used the cat paradox to challenge the Copenhagen interpretation, suggesting that quantum mechanics, while powerful, did not fully explain the nature of reality. The paradox of Schrödinger's cat has led to several interpretations of quantum mechanics, each attempting to explain how quantum systems behave and how we should understand the role of observation. One of the most famous alternative interpretations is the many worlds interpretation proposed by Hugh Everett III. According to this theory, all possible outcomes of a quantum event actually occur, each in a separate, non-interacting branch of the universe. In the case of the cat, the universe would split into two branches, one where the cat is alive and one where the cat is dead. Both outcomes occur, but they exist in separate, parallel realities. This interpretation avoids the problem of wave function collapse, but it introduces the idea of an ever-growing multiverse, which remains difficult to test experimentally and challenges our understanding of the universe's structure. Another interpretation is the de Broglie-Bohm theory, which suggests that particles have definite positions and velocities at all times, even when not observed. In this view, the wave function is a guide to the particle's motion, but it does not cause the particle's behavior to be probabilistic. The particle always exists in a definite state, but its position is influenced by a guiding wave. This interpretation offers a more intuitive, deterministic view of quantum mechanics and avoids the paradox of wave function collapse. However, it remains less widely accepted than the Copenhagen interpretation or the many worlds interpretation, and it faces challenges in terms of experimental verification. Schrödinger's cat is not merely a theoretical construct. It has had a lasting impact on the development of quantum technologies. The ideas it encapsulates, superposition and entanglement, are foundational to emerging fields such as quantum computing and quantum cryptography. In quantum computing, for example, qubits can exist in a superposition of states, allowing them to perform multiple computations simultaneously. This ability to process vast amounts of information in parallel makes quantum computers exponentially more powerful than classical computers for certain types of problems. Schrödinger's work on superposition, wave functions, and quantum entanglement provided the theoretical underpinnings for these advancements, which promise to revolutionize industries ranging from cryptography to artificial intelligence. The Schrödinger's cat thought experiment also continues to spark discussions in the realms of philosophy and metaphysics. The paradox it presents questions the nature of reality and the role of the observer in shaping it. Does reality exist independently of our perception, or is it only defined when we observe it? This debate goes beyond the confines of physics and has implications for how we understand consciousness, perception, and the nature of existence itself. The cat paradox, in a sense, challenges the very fabric of what we know about the universe, offering a window into the philosophical implications of quantum mechanics. It suggests that the nature of the universe is far more complex, uncertain, and intertwined with the act of observation than classical physics ever imagined. In conclusion, Schrödinger's cat is not only a fascinating thought experiment, but also a powerful tool for exploring the deepest questions about quantum mechanics and the nature of reality. The paradox encapsulates key concepts in quantum theory, such as superposition, measurement, and the role of the observer, and has become an enduring symbol of the strange and counterintuitive nature of the quantum world. While Schrödinger's original intention was to critique the Copenhagen interpretation, The thought experiment has had a lasting influence on both theoretical physics and the philosophy of science. It continues to inspire debate and investigation into the very nature of the universe, offering insights into the profound mysteries that quantum mechanics unveils.